Alright, our original function we have was x to the third minus 6x plus 1. We'll call it replace t with x from our sheet. That'll remember be in blue, so that will be the position function in blue. This is what I asked you to sketch on the bottom of your sheets. What's the derivative? What do I type in next?
3x squared minus 6.
Remember, that will be the velocity graph. First derivative. What's the second derivative, or the derivative of velocity? What's our next function look like? 6x. Good. Remember, that will be the acceleration graph. So blue is position, red is velocity, and black is acceleration. So let's look at these. In a standard viewing window. I might have to make it a little bit bigger, but we'll look at this first and see what we get when we graph them. Position. Velocity. Acceleration. Now let's see what happens. When the position function is increasing, the velocity function is above the x-axis. When the position function reaches a peak here, so in other words the slope is 0, the velocity is at 0, the slope. When I have a negative slope on the position function, the velocity function is below the x-axis. The function is decreasing there. And when I have again down here, minimum, the velocity function is at 0 because the slope right here is at 0. And when I'm increasing on the position function is when my velocity is positive or above the x-axis. So think in terms of you're actually walking along the graph, the blue graph. You're the position particle moving along the blue graph to see what happens as you're moving along the graph. So if you think in terms of direction and way that you're moving on the graph, we would be moving positive velocity, remember, means that I'm going to be moving either forward or to the right or upward, depending on the problem you're looking at. So here, I would be, let's say we're moving to the right for positive velocity and left is negative velocity. By moving to the right, and then I switch directions. Now, I'm decreasing, so I'm going to be moving, let's say, to the left. Now I switch directions, I stop and switch directions again, and now again I'm moving to the right. So think about how that works now with the acceleration graph, our second derivative. So when the velocity, let's think in terms of what we learned earlier. When the velocity and acceleration are both positive, the speed is increasing, and when the velocity and the acceleration are both negative, the speed is also going to be increasing. Well, you should be able to tell now from the graph where that is. Because look, the red is the velocity graph, and the black is the acceleration graph. So we can see where both of them are going to be positive above the x-axis, and we can see where both of them are going to be negative or below the x-axis. Okay, and then here's the other thing to look at. The derivative of the blue is the red. That should make sense because the derivative of a cubed function is a squared function. And the derivative of a squared function is just a plain old line function. Well, that makes sense because this black here line is just a straight line. But let's see what happens where the minimum is on the red, that's velocity, the slope is 0, is where the acceleration one here, the black line, is equal to 0. That makes sense as well. So we interpret it just like a derivative graph, the same as we've done before. Let's go to our problems and see if that all makes sense now when we look at the problems on the sheet. All right, our first question, find the displacement during the first 4 seconds. Can someone show us how to get the displacement? I'll let you, all of you come up and do the work on the board up here. Who's got it? I saw it on sheets. Who's got it? Show it on the board. Someone go up and do it. Thank you. Okay. And what's our unit?
Meters.
Nope. Read the question again.
Feet.
Feet. So 40 feet. Label it. I put labels on all of our problems. Thank you. So S of 4 minus S of 0. Think of displacement as where you are, everyone. It's your position. I'm standing here now. Where am I standing 4 seconds from now if I'm walking down the street? That's where you are, displacement from 0 to 4 seconds. In other words, it's not quite the idea of distance traveled. We'll talk about that when we do integration, not now when we do these problems, but it's the idea of where you are. That's all displacement is. How many feet have you gone from 0 to 4 seconds? All right, part B. Find the average velocity during the first 4 seconds. So someone show us how to do that. Mm-hmm. Thank you. Displacement divided by time. That's all it is for average velocity. So we're taking S of 4 minus S of 0 divided by 4 minus 0. We've already found S of 4 minus S of 0 in your first part for the displacement. And it's feet per second for average velocity. Okay, next part. Find the instantaneous velocity when t equals 6. So times 6 seconds. Someone show us how to do that one? Thank you. Label it. It's velocity, so how would we label it?
I couldn't tell you.
Help them out. And then one more thing. At the top, label it v of t and your original function that you found, which is correct. Label it v of t equals. I want you, everyone, to get used to the correct labeling. Thank you. For these problems. S of t is labeled position, or x of t again. V of t is velocity, and a of t is your acceleration function. Always label your functions. The next part, find the acceleration of the particle at time t equals 6. Someone show us how to do that? Thank you. Questions so far? Last part. What value of t does the particle change direction? Someone show us that part? What do we do to find out where the particle changes direction? Correct. Set the what equal to 0? Right. Instantaneous velocity. All you have to do is set that simple equation, which is right there, equal to 0, and solve it. Someone go up and solve it for us. Thank you, Allie. Someone give us a decimal for square root of 2 from their calculator. Gianna, you got your calculator right there in front of you. Give us a number for square root of 2.
1.414.
Okay, 1.414. The reason I'm asking is because let's go back now to our graphs on the graphing calculator for a moment. And the question was where the particle changed direction was at 1.414 and negative 1.414. Is that not where we looked at earlier, where the particle was going up or increasing, or to the right, stopped and then changed direction, stopped and then changed direction? And isn't that exactly where these are equal to 0 and cross the x-axis? Should make sense, right? It should make sense logically when you look at the picture and graph of it. It should make sense with the calculus and the math that you're solving and the picture. So if you solve it and it doesn't have a velocity of 0 at those values, then it means you solved it incorrectly. Go back and recheck it. You will have problems where you'll just look at graphs and interpret graphs. You'll have problems where you look at functions and evaluate functions, and then you'll have some of both. On this one, I think when we start learning the particle motion, it's really important that you look at the problem functions and graph them, as well as look at the actual functions themselves and solve them algebraically after you take your derivatives. Questions on the sheet?